When you pour a glass of water or fill a car with gasoline, you observe that water and gasoline flow freely. But when you pour syrup on pancakes or add oil to a car engine, you note that syrup and motor oil do not flow as easily. The viscosity of a liquid is a measure of its resistance to flow. Water, gasoline, and other liquids that flow freely have a low viscosity. Honey, syrup, motor oil, and other liquids that do not flow freely, like those shown in Figure 1, have higher viscosities. We can measure viscosity by measuring the rate at which a metal ball falls through a liquid. The ball falls more slowly through a more viscous liquid. Or by measuring the rate at which a liquid flows through a narrow tube. More viscous liquids flow more slowly. The intermolecular forces between the molecules of a liquid, the size and shape of the molecules, and the temperature determine how easily a liquid flows. As the table below shows, the more structurally complex are the molecules in a liquid, and the stronger the intermolecular forces between them, the more difficult it is for them to move past each other, and the greater is the viscosity of the liquid. As the temperature increases, the molecules move more rapidly, and their kinetic energies are better able to overcome the forces that hold them together. Thus, the viscosity of the liquid decreases. So again, this is showing you a chart of the viscosities. Just the higher the number, the more viscous the liquid. The lower the number, the less viscous the liquid. The various intermolecular forces between identical molecules of a substance are examples of cohesive forces. The molecules within a liquid are surrounded by other molecules and are attracted equally in all directions by the cohesive forces within the liquid. However, the molecules on the surface of a liquid are attracted only by the liquid. However, the molecules on the surface of a liquid are attracted only by about 1/2 as many molecules. Because of the unbalanced molecular attractions on the surface molecules, because the stuff above them is air, liquids contract to form a shape that minimizes the number of molecules on the surface. That is, the shape with the minimum surface area. A small drop of liquid tends to assume a spherical shape, as shown in Figure 2, because in a sphere, the ratio of surface area to volume is at a minimum. Larger drops are more greatly affected by gravity, air resistance, surface interactions, and so on, and as a result are less spherical. So you can see the intermolecular attractions attracting these molecules in all directions except for pulling upward because they're at the surface. Surface tension is defined as the energy required to increase the surface area of a liquid, or the force required to increase the length of a liquid surface by a given amount. This property results from the cohesive forces between molecules at the surface of a liquid, and it causes the surface of a liquid to behave like a stretched rubber membrane. Surface tensions of several liquids are presented in the table below. Among common liquids, water exhibits a distinctly high surface tension due to strong hydrogen bonding between its molecules. As a result of this high surface tension, the surface of water represents a relatively tough skin that can withstand considerable force without breaking. A steel needle carefully placed on water will float. Some insects, like the one shown in Figure 3, even though they are denser than water, move on its surface because they're supported by surface tension. So again, this is a measurement of the surface tension of different liquids. The higher the number, the greater the surface tension. The lower the number, the less the surface tension. The intermolecular forces of attraction between two different molecules are called adhesive forces. Consider what happens when water comes into contact with some surface. If the adhesive forces between the water molecules and the molecules of the surface are weak, compared to the cohesive forces between water molecules, the water does not wet the surface. For example, Water does not wet a waxed surface or many plastics, such as polyethylene. Water forms drops on those surfaces because the cohesive forces, those are the forces that attract water molecules to other water molecules, within the drops are greater than the adhesive forces, the forces between the water molecules and some other surface. So the adhesive forces between the water and the plastic. Water spreads out on glass because the adhesive force between water and glass is greater than the cohesive force within the water itself. When water is confined in a glass tube, its meniscus has a concave, that means dipped in, shape because the water wets the glass and creeps up the side of the tube. On the other hand, the cohesive forces between mercury atoms are much greater than the adhesive forces between the mercury and the glass. Mercury, therefore, does not wet glass, and it forms a convex meniscus when confined in a tube because the cohesive forces within mercury tend to draw it into a drop. So convex would be like a bulging upward as opposed to that concave meniscus that you're used to seeing with water in a um, graduated cylinder. So this is a picture of mercury and water in a graduated cylinder. Notice the convex shape of mercury because the attraction between the mercury molecules are stronger than the attraction between the mercury and the glass. And then with water, notice that forms a concave shape or a dipped in shape because the adhesive forces or the attraction between the water and the glass tube are stronger than the attraction between the water molecules or those cohesive forces.